In this video, I introduce a Phenaki foundation world model for video generation from textual prompts. Phenaki is a text-to-video synthesis model given a sequence of textual prompts, which consists of two major components, namely an encoder-decoder model to compress videos to discrete tokens, and a transformer to translate text embeddings to video tokens that are converted back to the pixel space. The encoder compresses a video sequence of tx plus 1 frames with a resolution of wx by hx and cx channels, as shown here. This frame 0 and this frame tx, this wx, and this hx, into a token representation of size tz plus 1 by wz by hz, as shown here. This wz, this hz, where the first wz by hz tokens represent the first frame independently from the rest of the frame, and the remaining tokens represent spatial temporal video tokens that autographically depends on the previous frames. As shown here, the first frame is independent, and the rest of them depend on its previous frame. To this end, the non-overlapping image patches, WP by HP by CP, as shown here, this WP, this HP, are extracted from the first frame, and the video patches TP by WP by HP by CP from the rest of the video, as shown here and here. Each patch is flattened into a DZ dimensional space, and then the flattened tokens are combined as a tensor, DZ plus 1 by WZ by HZ by DZ with separate spatial and temporal dimensions. As shown here, as a single patch is flattened into a DZ dimensional vector, and this single frame is flattened into 4 DZ dimensional vectors. Put all them together, we get a codebook CZ. A spatial transformer is applied on the tokens of the single frame, followed by a spatial temporal transformer with a causal tension in an autographic manner. This opens up a probability of text-to-image training to be embedded naturally into the video model. The resulting patch embeddings Z of the shape TZ by WZ by HZ by DZ are then tokenized into learned code words CZ by vector quantization. The decoder is an upside-down version of the CVI-VIT code structure. First, the tokens produced from the encoder are transformed into embeddings, and then the spatial temporal transformer followed by the spatial transformer. A single linear projection without activation is applied to map the tokens back to the pixel space. To learn a discrete latent space, the encoder outputs are quantized into the entries of a learned codebook via the vector quantization objective as shown here, where SGX defined as X and 0 derivative is the stop gradient operator. Beta is the commitment loss weight, and E is a codebook vector from codebook E. The index to the codebook vector closest to Z is found by the R minimum. The model total loss L is defined as a weighted sum of L2 loss, image perceptual loss, video perceptual loss, and adversarial loss, as shown here. Masked bidirectional transform predicts different video tokens simultaneously. For training step I, a mask ratio gamma I from 0 to 1 is sampled, and the gamma I by n tokens are randomly replaced with the special token mask, where n is the video sequence length. The model parameters are learned by minimizing the cross-entropy loss on these masked tokens given the encoded text embeddings and unmasked video tokens. At each inference step, the masked video tokens are predicted in parallel condition on the text embeddings and unmasked video tokens. A ratio byte I of the predicted tokens at the sampling step I and the remaining tokens are remasked and repredicted in the next step. Masking schedule gamma I and the sampling schedule beta I have a significant effect on the sample quality. More sampling steps improve the quality. During the training time, the encoder-decoder model uses the masking method to learn the codebook in a self-supervised manner, while during the inference time, inspired by diffusion probabilistic method, the spatial and spatial temporal transformers use the scaling function with the masking method to generate each video frame gradually. As shown here, for example, this Foster frame, this spatial transformer, we get output attention distribution. And then we use this output as an input together with the masked distribution and this embedded prompt together as the input to spatial temporal transform together Foster output. And then we follow this mask ratio gamma I step by step, get a final prediction. The pre-trained CVI-VIT encodes video into codebook IDs A of shape TZ plus 1 by WZ by HZ, zeta flattened into a long vector using the raster ordering. The text conditioned video token distribution is modeled by using masked visual token modeling, as shown here, where A M bar is a masked version of A. MI is a binary variable indicating whether AI is masked or not. N is the number of video tokens, and P is a text condition embedding. Here is a Phenaki architecture. This details of CVI VIT encoder. Here's the details of training transformer, and this details of video generation. For more details, please check with these references. Thank you. Bye.